Here we're told we have water coming into a cylindrical tank of diameter d, and it's coming in with a volumetric flow rate Q1 here, volumetric flow rate Q2 here. It's going out with an average velocity of v bar 3 through this cross-sectional area A3. And we're told that the level of water in the tank is changing with time, so h is not a constant. And we're asked to find that time rate of change of the level of the tank. So we want to find dH dt, how that height is changing with time. So what I'm going to do is I'm going to draw a control volume that surrounds the water inside the tank and apply conservation of mass to that. And the reason I'm applying conservation of mass is because I know the mass inside this control volume is changing with time. Now this control volume that I've chosen is going to be a deformable one, meaning it's going to move with the free surface here. So as that level of water goes up, the control volume also goes up. Okay, so it's not a fixed control volume. That's totally fine. You can make your control volumes do anything you want. So we'll write out conservation of mass. Time rate of change of mass inside the control volume is equal to the rate at which mass is coming in minus the rate at which mass is going out. Let me just focus on the mass flow rate coming in first. We have mass flow rate coming in here and here. These are volumetric flow rates, so to get a mass flow rate we multiply by the density. And then the mass flow rate going out, there's only one spot where it's going out, and that's right there. Remember, it's not going out through the top because I have a deformable control volume that's changing as water comes in. It's just staying with the level of the water. So the only place it's coming out is right here, and to get that mass flow rate, that'll be the density of the water times its cross-section. This is the average velocity through the cross-sectional area A3. And I'm assuming that the water is incompressible. Let me go ahead now and address the time rate of change of mass inside the control volume. So that'll be equal to the time rate of change of the density times the volume of the control volume, right? So you can get mass by just taking the density times the volume of the control volume. Since the density is a constant, since we're assuming water is incompressible, it'll just be the density times the time rate of change of the control volume. And the control volume is going to be just the volume of a cylinder. It's going to be the cross-sectional area, pi capital D squared over 4, times the height. Right? This is just the volume of this cylinder. And of course the diameter of the tank isn't changing with time, so I can pull that outside. So pi d squared over 4 comes outside, and so I'm left with dH dt. This is what I'm trying to actually solve for. So you can see, let me go ahead and rewrite the full expression for conservation of mass with all this information there in one equation. There's the time rate of change of mass inside the control volume. Here's the rate at which mass is coming in. And then here's the rate at which mass is going out. And you'll see that there are densities in all of these that we can cancel out. And then we can solve for dH dt. And that is just some simple algebra there. So there is the time rate of change of the height of this level here as a function of, so that's just how that height level is changing with time. So this is just a straightforward application of conservation of mass. The only thing that's a little bit tricky here is just choosing your control volume. I chose one that was deformable. By the way, you don't have to do that. There are other control volumes that you could use, but I just chose one that was deformable because that seems the easiest. And then recognizing that the mass inside the control volume is like the density times the volume, and the volume is just the cross-sectional area times the height. So that's how I bring height into the problem. And then recognizing that density and the cross-sectional area remain constant with time. Okay, we'll end the example there.